Today we're going to introduce ourselves to the Gauss-Seidel method. Okay. And before we do that, let's just get what the answer is to this system so we can compare it with what we get when we use Gauss-Seidel method. Okay. So I'm just going to do A backslash B, and why don't we take a look at this solution. There it is, minus 5, 0, 0. Okay. All right, and if we want to start implementing this technique, okay, is what we want to do is we want to solve for x1, solve for x2, solve for x3. Okay. So we'd have x1 is equal to, okay, and so we'd have to add the 3x3 to the other side. I'm going to need my multiplication sign there. And then also note that there's this b over here, so I'll have a minus 2. And then I need to divide by 4. Okay. And then we'll want to do the same thing for x2. Okay, so if we take this second equation and solve for x2, we're going to have to add a 2x1 to each side. We'll have to subtract a 4x3 on each side. And we'll need to account for this 1 that's already on the other side. And then finally, we'll need to divide this all by 5. That way we can officially solve for x2. And then one more, we have x3. All right, and so here it looks like we just need to move over a minus 2 x2, and the constant that's over there is just a 0, so all we have left is just divide by 3. All right, and I'm going to go ahead and suppress these. All right. And let me put in one more comment here. And I want to make a comment about this diagonally dominant phrase here. Okay. So what that means is that the diagonal elements, they're larger than everything in their row. Okay. So you can see this 4 is bigger than the 0 and the minus 3. The 5 is bigger than the minus 2 and the 4. And the 3 here is bigger than the 2 and the 0. Okay. So this is considered diagonally dominant. Okay. Now, it is not required for the system to be diagonally dominant for this method to work. But when it is diagonally dominant, it guarantees that it will work. Okay. All right. Well, let's keep going here. So the idea, okay, and we normally probably want to do a while loop and have this thing run until the relative error is within some desired value. But just to get an idea of how the method works, let's maybe just start off with just a couple iterations. Okay. And actually, I think I might even unsuppress this. Okay. For now, let's do just 3 iterations. And let's also note our answer. Let's make it just a vector. So how about x1, x2, x3? Okay. All right. And the last thing we need to do is, you might have a question, is this for loop going to run as it is? The answer is no, because to compute x1, we're going to need an x3. Okay. And we could take a complete guess on x3, or if we actually have an idea of what x3 is, it'd be better to use that estimate if we have a decent idea. But for now, let's just pretend we have no idea, and we'll just say 1. And then when you get down to the second equation, we will have an x1, we will have an x3. And for the last one, we will have an x2. It'll be computed in the line above. So I think this might be all we need here. Okay. Let's go ahead and we'll give this a run and see what it looks like. Okay. All right, so we had the answer, the actual answer is minus 1/2, 0, 0. Okay. And you can see with our first iteration of this technique, we get minus 0.25, minus 1/2, 1/3. So this isn't looking very accurate after the first iteration. Okay. And then it looks like we have minus 1/4, minus 1/6, and then 0.1111. But if you look at this third iteration, it's starting to get closer. X2 and X3 are actually getting pretty close to 0. X1 is getting close to 1/2. Okay. And then here's our vector that is our answer from this technique. But we've only used 3 iterations. Let's bump this up to 10, see what happens. Okay, and actually I'm going to suppress all this as well, although you can see the answer right there that we just got from this technique. If I suppress that, we can see both our answers side by side without me moving the command window too much. Okay. All right, there they are. The backslash command and with Gauss Seidel, it looks like we have the same answer. Let's just take a look at maybe a few more decimal places. Alright, still looks pretty good. Especially if we maybe up this again. Let's see if we can get a little bit closer. Let's try 100 iterations. Okay. So after 100 iterations, it looks like they are going to be close to, if not identical. Yeah, they are identical. Okay. Alright, but I want to talk more about this diagonally dominant portion. Again, it does not have to be diagonally dominant for this to converge, for this technique to converge on an answer. Okay. But if it's not diagonally dominant, it is not guaranteed that we will converge. Okay. And so I want us to look at one more example where it's not diagonally dominant, and we'll see what happens. So here we have almost the exact same system. Okay. And in fact, maybe I could start off by saying answer using backslash, and we'll say ans1 is equal to a backslash b, and we can take a look at this answer here as well. There it is. Okay. And let's start trying to set up this technique. So Gauss, Seidel, implementation. And so we need to do the same thing here again. We need to solve for x1. So I just need to add the 3x3 to the other side. I already have a minus 2 over there, and since this is just a 1, I don't need to divide both sides by 1. Solve for x2 in our second equation. So we get x2 is equal to 2 times x1 minus 4 times x3. And then we have a constant that's on the other side, so I also need a plus 1. And then x3, which is equal to 2 times x1. Oh, sorry. X3 is equal to minus 2 times x2. there's no constant, and so this is actually it for x3. Okay. Go ahead and we'll suppress that, and we'll set up a for loop just like last time. Okay, which again, we would normally want to probably do a while loop where we can say that we want to get within some desired range of values, or some desired relative error is what I mean. Okay, so we have I equals, let's just do 1 to 8. I think that'll be plenty of iterations for this example. Okay. Now before I run this, we need to make sure everything's defined. So to compute x1, we're going to need an x3. So how about we just do the same thing here again? How about x3 equals 1 as a guess, and then x down here, it looks like we're going to need an x3, which we'll already have picked one. Looks like we'll need an x1, and that'll be computed in the line above. And then down here, we'll need an x2, which was computed in the line above. Okay. But all that's happening is we're really just substituting in values for x1, x2, x3, and they're being updated, and then we substitute them in again, they're updated, substitute them in again, they're updated, and somehow this gets closer and closer to the correct solution. I should say not in all cases, but in the cases where it converges, it's going to get closer and closer to the solution. Let's see if we get convergence here. Okay. So maybe we should do ant2 is equal to x1, x2, x3. There we go. All right, and you can see this is not converging. Okay. And I could choose to do more of these, except for I have a feeling those numbers are gonna. Ooh, are we getting closer? Let's move this up a little bit and see how we're doing. Oh, it looked at first glance like we were getting closer before I saw the 1 times 10 to the 11. Okay. But yeah, we are way off now. We are way off. Those numbers are times 10 to the 11. Okay, not even close. We have a third example here, and let's go ahead and run it, see what the answer is. And there it is. 0 minus the third and 2/3. Okay. And if we were to try to set up the system of equations here, is what we would find using the Gauss-Seidel method is that we'd have divergence here. And maybe we should just set it up real quick just so we can see it. Okay. So if we were to do this, okay, we'd have our little for loop. And then for our first equation, we'd have x1 is equal to 3x3. For our second equation, we would have x2 is equal to 4 times x1 minus 2 times x3. And I shouldn't forget about my b vector over here. I should have a minus 2 over here and a plus 1 here. Okay. And then next I'd have x3 is equal to minus 2 times x1. And actually that should be x3 is equal to minus 2x2, and then the b is 0. Okay. Let's go ahead and end this. And let's make sure we've defined everything we need in order to make sure that the for loop can actually run. So let's see, x3, let's just set that at 1, and that should be all we need, because in the next line we just need x1 and x3, and we'll have computed x1 and we were given x3. So that should work perfect. Okay, let's go ahead and just set up our answer. Okay, so x1, x2, x3. Okay. And if we run, let's see what we get. Okay. Very different answers, right? The second one is times 10 to the 12 times those values. So yeah, these are way off. Okay. But what if we rearrange our equations here a little bit? Okay, we're going to rearrange this system. Let's maybe call this A1 and this B1 and okay. So we're just going to rearrange this a little bit. So maybe I'll call it A2 and B2. And which means that maybe we'll call here this A2B2. So that's what we're going to be interested in. We could even comment this out. We don't need it anymore. And I'm going to rearrange this so that it is diagonally dominant, if I can. Okay. And if we look here, this is the biggest diagonal in column 1. So it would be nice if this was in row 1. Let's do that. Row 1. Okay. And the 2, if this was in row 2, then this 2 would be bigger than everything in its equation, and it's on the diagonal. And then finally, the absolute value of -3, this is now bigger than everything in its equation. The only other thing we want to do here is maybe put in our semicolons and our bracket. Okay. But also we need to rearrange B, right? These were equations. B is part of that equation. So we moved row 3 to row 1. Okay, so that means that this is going to be a 0 here now. We moved actually, let me rephrase that. We moved, it looks like, in place of row 1, we have the old row 2. Okay. So the old row 2, we need to put the 1 here. I'm going to just delete both of these. Okay. If we move down to row 2, 0, 2, 1, this was originally in row 3, so that means this 0 here needs to move up to row 2. Okay. And then finally, the last row in A here is came from row 1. So I want to bring this -2 down here. I'm going to call these, again, B2, A2. Okay. And we should be able to solve this system. But let's again write down our new equations down here and see if we can get this to converge. Okay. So if we were to do that, starting off with the first equation, we would have, start moving stuff around. We need to move over a -x2. We'd also have to subtract by 2 times x3 on each side. And then we still have the value of b here, so +1. Okay. Then if we go down to the next equation, oh, actually, we weren't quite done. We still needed to divide by something. In front of x1, we have this -4, so we want to divide by -4. Okay. All right, and then we have our second equation here. Let's edit it. So this looks like x2 should be equal to -x3. Okay, so -x3, and then divided by 2. Because we didn't have a b value to work with here. Okay. And then finally our last equation, we should have x3 is equal to positive 3 times, let me fix that. We should have x3 is equal to, and we need to subtract by x1. Okay. So that's done. We also have a minus 2 that's over here. And then we want to divide this all by the number in front of x3, which happens to be minus 3. Okay. All right, let's go ahead and give this a quick run and see how we did. Uh-oh. I'm guessing we haven't defined everything that we want to up here. So x1 is going to be dependent on x2 and x3, so I need an x2 in here as well, as a guess. Okay. Let's give that another try. All right. And it looks like we're converging on the correct answer here. And if we wanted to, of course, we could, right, do more iterations. Let's pull that up. Okay. All right, these are looking pretty much the same. So do keep that in mind with the Gauss-Seidel method. If you're not getting convergence, sometimes just rearranging things can make that convergence happen. Okay. And that is it for today. We will make an attempt to create a function that implements this technique Friday.